Hello and welcome everyone to my today's session. My name is Farid Pasha and I will be giving you a brief introduction on neural networks in Wolfram Language today. So how I have paced my session today is I will first talk about why neural networks are important, what they exactly are, and their building blocks. Then I will demonstrate how to train the neural net, also known as deep learning. We will also take a deep look by developing an image classifier, and we will see it in action in some other applications like image segmentation, style transfer, as well as in object detection. I will also touch base on Wolfram Neural Net Repository and how you can take advantage of that as well. So, if you have not used machine learning, deep learning, or neural networks yourself, you have almost certainly heard of them. They are everywhere. You may be familiar with their commercial use in self-driving cars, image recognition, automatic text completion, text translation, audio analysis, or even in complex data analysis. But you can also train your own neural networks to accomplish tasks like identifying objects in images, generating sequences of text, or segmenting pixels of an image. So, with the Wolfram language, you can get started with machine learning and neural nets faster than you think. Since deep learning or neural nets is everywhere, in today's session, I will explore with you what exactly they are and how you can start using them. So, what exactly are neural nets? They are one of several programming approach to machine learning basically, which is inspired by the neurons in the human brain and that enables computers to learn from observational data, be it images, audio, text, labels, strings, or even numbers. According to MIT News, it was first proposed in 1944 by these two researchers, Warren and Walter, from University of Chicago. And the modern term used for neural nets is differentiable programming. And you will see today in my upcoming examples as why it is called such. So let's start and look at what are some of the basic blocks of the neural networks. So they are not that complicated. In reality, they are much simpler than people imagine. So you are seeing a simple neural net, which is basically a basic LeNet model, which is used for computer vision. So you can see that this network is built up of an input, then some layers, and then at the end, there is an output. So this is basically the framework architecture of a neural net we'll be discussing today. So let's move forward and see each of them in a bit detail. So the simplest building blocks of neural nets are layers, which you can think of as simple functions that transform arrays of numbers. So, for example, in this net is composed of a variety of layers, such as convolutional layer, polling layer, ramp layer, and each of these layers accomplishes a certain task. In this case, combining, they are performing the task related to computer vision. Let's take a look at the last layer, and I can use a function called net extract to get the last layer. We can see a lot of information about this layer. For example, it is Softmax layer, and I can open it and I can see that it expects a vector of length 10 as an input and returns the same. Like any layer, we can give an input. So it is expecting a input of a vector 10. So I can give any input to this layer and I can get the result or the output coming out of that layer. A layer can also accept a numeric array as shown in this example. So for example, I can pass it a numeric array and it will give me the output for that. The purpose of basically a soft max layer is to produce probabilities that sum to 1. And we can confirm that by taking a total of our last output. And we can see that it's a sum of the previous output, which are the probabilities, because that's what the softmax layer does. So now, how do you construct your own layers? So here's an example of creating a linear layer that takes as input a vector of length 2 and produces an output vector of length 3. So when I create this layer, I can click on this summary box and you can see that it takes a matrix of 3 by 2. Input port takes 2 vectors and output port is giving size vector 3 as I defined. You will also notice that here there is an uninitialized caption, which is indicating that the net contains learnable parameters or weights that have not yet been provided. So what will happen if I provide an input to this layer? Of course, it will fail because I have not yet initialized this layer. So any layer which has the symbol like this icon in the display form can be, for example, convolutional layer or linear layer have learnable parameters where you can define the weights. Whereas all other layers which has an icon similar like this do not contain any learnable parameters. So there's a function in Wolfram language called net initialize, which can be used to initialize a layer. We can supply an input now to this layer, and then you can see it has given us the output after initialization of the layer. We can also get the weights and the biases of these layers. And because they are like numeric arrays, you can always like maybe take a normal of this last and you can get the weights values over here also as well. So up till now, we have seen layers that have exactly one input. Some layers have more than one input. For example, mean squared loss layer. So basically, what it does, it compares two arrays called the input array and the target and produces a single output that represents mean or loss in terms of neural nets. The inputs of the layer are named and must be supplied in an association when the net is applied. So here I'm applying an association of input and the targets to this layer, and I can get the output of the layer. Here is a full list of layers which are available in Wolfram language. While some layers introduce functionality that is unique to the neural net framework, others mirror the functionality of existing Wolfram language symbols. For example, the flatten layer behaves similarly to flatten function, or dot layer behaves similarly to a dot function in Wolfram language. Before moving further to other building blocks, I would like to share some more key properties of neural net layers in the Wolfram language. So layers can be run on either a CPU as well as GPU. So you can define by the target device. But I only have the CPU. I do not have a GPU, so I can only show you a demonstration. Otherwise, if you have a GPU, just you need to mention over here is GPU and run this on the GPU device. Layers also perform shape inference. So, for example, if the dimensions of the input are specified, then the layer can infer what the dimensions of the output will be. So, for example, here I am giving it the dimensions. That is, it has to be a 4 by 32 matrix. It will automatically infer that the output will be also of the same dimensions. Similarly, layers are differentiable. So, as I mentioned earlier, differentiability is a key property that allows for the efficient training of nets. And here in the below example, you can see that the outputs are the same, whether I pass it the same vector through a layer or a differential function. So the first is a layer and the second is a simple differential function for the similar input. And you can see that the results are the same. Similarly, layers are functions whose inputs and outputs are always arrays or scalar. Now you must be wondering, you want to use some image or you want to use an audio, then how the layers can only take scalar input or output, how it will work on those things. So for that, we have to develop net encoders, which are normally attached to the input. And that brings to my next section, which is regarding another building block, which is net encoder. So let's take a look at an example of this encoder in action. So for example, we have to develop an image encoder that converts this image into a matrix. So we can see that the dimension of this image is 236 by 213 matrix. So our input has to be defined accordingly. So I'm defining a net encoder, which will have an image and the dimensions will be 236 by 213. And when I define this, you can also see the same details as here, where it has an image, the image size, and the output is an array of 3 ranks. Why 3 ranks? I'll tell you in the next slide maybe. We can apply the image encoder to that image, and you can see that we can get the array or a scalar thing, which we can now use in our net. And I've saved this as an variable here because when I'll show you the decoder development, we'll use this same. So you can attach encoder to the layer also. You don't have to just define it separately. You can also attach it directly to the layer. This can be done just by creating a layer and afterwards just attaching the encoder to that layer. Now let's take a look at the net decoders. So for those outputs of the net, which is basically a prediction, for regression problems, this prediction is typically a point estimate, which means it is a single number representing the value the net thinks is most likely to happen. Such outputs do not typically need to be decoded. However, for classification problems, the output of the net is typically a vector whose components represents the probability of each class. For example, a net that classifies images of foods as hot dog, pizza, or salad produces a vector with 3 components that sum to 1, representing the probabilities of those 3 classes. So let's For those kind of probability vectors, we have to develop the net decoders, which can take the vector input and then based on those raw probabilities, give us the classes. So here I'm defining a net decoder which has these three classes. So normally the dimensions of the net encoder are equal to the classes in your architecture. And you can use it on a probability vector. So for example, this probability vector comes to this decoder, and based on that, it can say that, okay, this is going to be a B class. You can also see the top probabilities, what the decoder receives. And we can also the net decoder for or we can see the losses. And here I'm creating a net decoder for the image, which we did in the previous section. And when I pass that to this, I can get the image back. So layers, net encoders, net decoders, three things. Next, we will take a look at the containers. So containers, basically, why are they used? Because single neural net layers are generally not useful by themselves. We usually need to combine multiple layers together to do something interesting. So the simplest way to combine layers is to chain them one after the another, where the output of the first layer is used as the input for the next layer and so on. We can use the net chain container to connect that type of layers. So you can see I have one layer. The output of this layer will go as an input of this layer. The output of this layer will go as an input to my output. And you can see that, like, if I pass in the same thing in the chain, which is basically a map of two functions, or if I map those two functions together in Wolfram the language, the results are the same. Another important property of container is that they act as layers and can be used as layers. So for example, I developed or I made an architecture of a layer chain, and then I can use that chain in another chain like this. So I have one layer, two layers, and then I have a chain which contains another two layers. So I can use this chain property as well. But most of the time, things are not as simple, like one after the another. We might have a different configuration of the architecture. So for those type of instances, net graph can be used, which is to connect different layers to create a graphical neural network. As you can see that in this, the layer 1 is connected to 2 only, but 1 and 2 both are connected to 3. So this is not like a chain, this is like more like a graphical combination of the architecture. So one more constructor I want to mention here is net port, which basically represents the specified port for a layer in a net graph or similar structure. But when you have multiple layers as inputs and outputs, normally this type of container is more useful. So here is an example. You can see here I have two outputs. One output is labeled as sum, and the other output is coming with the label output. So net port is useful in these type of architectures of layers. So now we know most of the basic building blocks. We have the layers, we have the containers, we have the encoder and the net decoders. Now we have to train these nets. So we know that basically the neural nets are data-driven algorithms. You can think of training data as simply specifying a function where training tunes a net to approximate this function. So we have this example that contains list of rules. This is my data, and this is my architecture where I'll have an input, a target, couple of layers performing certain functionalities, and then I'll have the loss coming out of there. And I have initialized this net already. So once you have defined the layers, I can just pass an input into that and see what happens. So you see I get a result. But this is just randomly giving me a result because up till now, I have not yet trained my system. So the function used in Wolfram language for the training is called netTrain. So in this example, I'm using the netTrain function. I'm giving as an input my this architecture and the data on which I need to train my system. So when I execute this, this will train my neural net. It shows me how much time is take, how the validation is going on, which method is used on, and it can give me the trained net. Now, when you see, when I pass the input and output, same input and output now to the trained neural net, it give me a very small value as compared to others because now my neural net is trained and I can see the weights of the both of the systems without training of and after training. So you can see the weights have changed. And that is why I get a more accurate result after training. So this is how the neural nets are developed and are created in Wolfram language. So let's move forward, and now we will basically perform some deep learning on some images. And for that, we'll be developing a image classifier neural net. So as neural nets, are data driven. So we have to start from some data to train our neural net. So for speed and simplicity, what I'm using is a CIFAR10 dataset, which is basically a dataset made by Canadian Institute for Advanced Research in Toronto, which consists of 50,000 small color images of size 32 by 32, which are donated in and which are classified in 10 different classes. And CFR10 is also available as a Wolfram resource, so I can directly get that data into my notebook as a resource object. And here I can divide that data, a portion of that data into a training data and a portion of some data into my test data. And I can also see what the classes are. So this is how the random sample of the training data, so these are 32 by 32 pictures, and they are associated with certain classes. And we can see all those 10 classes which are available in my dataset. So now we have the data. Next is to construct the building blocks. So let's start with net encoder and net decoder, which will basically be converting the incoming image data into arrays, which we will feed into our layers, and then those layers will give us an output in form of an array, which our net decoder will use to decode into the image output of the class. So similarly as before, defining the net encoder image, here we know that the images are 32 by 32 size, we do that. And the net encoder is defined. And we can also pass it a picture over here and see it has converted into a output over here. Let's think I didn't. So I can see it is a 32 by 32 array. which I can now feed into my system. Similarly, I can define a net decoder, which will have now classes, and the classes are, these are those 10 classes. So my vector size over here will be 10. And here I can see that in a small example, if I pass a 10 probability of a 10 vector, it will give me the result. Let's here. So we have now defined the net encoders and decoders as well. Next is to what type of layers we need to have into our neural net. So designing a new neural network from scratch can be error prone. So normally what I prefer is start by something with by a established network architecture and then make improvement into that. So I know this is about images, so I can start with a simple LeNet architecture. And I just modified that based on my net encoder and decoder so that the inputs can be defined as per my data. So each layer is a function over here that processes an array of data. And I can get all of these layers into a chain. And I can see that they are like all arrays. And you can see that the input array is usually of rank 3. So the first rank is for the color channel, and the two other ranks are for the spatial dimensions, which is 32 by 32 in our case. Similarly, the output array is a list of rank 1, and the dimensions are equal to the number of classes. So now we have defined the net chain also. Let's go forward and train this data. So what I'm using, again, the net train, giving my layers, the training data. I'm using the testing data as a validation set, and I'm telling it that I need to have like maximum training rounds of 6, and my target device is CPU. And I can like execute this over here. And you can see that it has started processing data from my input port, and it has started to train my neural net based on my architecture I have mentioned over here. So while training is in progress, I can see from here what is the progress of my network going on, how many examples have been up till now evaluated, how much time is elapsed, how much time is left, what is the rate of examples per second, which method, because I have not defined any specific method. So based on my input and the other architecture, Wolfram language, automatically comes up with the most optimized model for this. And I can see how my model is being developed over here. So let's keep this model running and in the meantime, we can go into the net train in the documentation section, and I can show you what other options are available. So all these options, you can define them during the training. Like if you want to define the batch race, learning rate, how many maximum training rounds you want to do. Similarly, the methods you can define. If you have any target device like CPU or GPU, performance goals you can mention over there. So all of these options are available for you while performing the net train. So here there are some other properties which you can see of your trained model, and I will show you a couple of them, how to see the losses and the weights of your trained model over here. So all these properties of the trained model you can get once the model is trained. These are the possible 4 methods which are available. So ADAM is used for this specific case. So all these, most of the features, options, properties you can get from here, you are mentioned in the net train documentation center. How I go back to my okay. So it's still training. So I'll stop this training. I can stop my training from here also at any stage, but if I can keep on running this, it will complete it. So for example, once the model is trained, so what I have done, I have before the session, I've already trained this model, and we can go forward and I can show you how the full trained model looks like. So I can see the losses or the error rate. I can also see the loss validation from here. I have the confusion matrix plot from here, as well as the accuracy. So based on these properties, I can come up with my interpretation of the trained model. And looking at these graphs only, it seems that the validation data and the training data is diverging, which is giving me an idea. And the accuracy is also only 70%, which gives me an idea that my model is overfitting. So I need to perform certain types of optimization to get a better result of my neural network. So let's go forward. And what I'll do over here is now start optimizing my layers. So in the start, you might have seen I have a couple of layers. Now I have added more layers, which will remove the overfit of this model. I'm including a padding layer. I'm also using an image augmentation layer so that I could have more views of the same image over here with their reflection probabilities, because some images might have a reflection there and I need to take care of that to get a better results. And based on that, I can use some other layers like flattening of the layer or some dropout layers, so that some of the data which is not validated probably can be removed from the training data, and again the similar netput and output, and I can use that as the get the new neural net, optimized neural net. And then now based on this new optimized layers, which in this case a lot number of layers, I will then train this model. So in the second optimized way, what I'm doing, I'm also increasing the batch size. I say, okay, maybe the 6 batch size is not giving me a good validation results. Let's increase the batch size also. Let's also increase the training rounds. And I'll not train this system here because it will take a little time, but you can see from the graph over here how the validation rate and the loss is matching over here. And I can show you more clearly in the next similar examples. So here you can also see the validation error rate has decreased. The final rate has also decreased approximately. Oh, by chance, they are exactly the same. As well as the accuracy of this neural net is also increased. And I can also see from the matrix confusion matrix plot that I'm getting a much better result over here. And this way, I can start from a basic architecture and I can add the layers into that. I can modify my neural net as per my requirement and I can develop that. And at this time, I also want to show you the Wolfram Neural Network Repository. So basically what this is you can see that there are many neural nets models are available here. You can browse them by domain like audio, image, numeric, text, or you can browse by task type, and you can go over there and you can learn about centered models. So which some of the neural net models are also already available over here. So maybe if you think that you want to develop a neural net which can be similar to like this. So for example, in my example, I started with a simple LeNet model, and then I kept on added certain more layers into that to develop a more better image classification neural net. And if you click on any of here, you can see more information over here. How many, what the model is. You can also download the example into your notebook, and then you can learn more about this. You can see what this model is doing. Basically, it's just converting the zebras into horses, what the net information is available, You can adopt it to different sizes. So all of these neural nets are available at this Wolfram Neural Net Repository, and you can also add to that. So if you develop something, you want that to be added and shared with other people, you can let us know and we can help you in adding that repository here also. So for example, so what I'm doing over here is just uh, uh, importing the same model from the repository, and then just displaying and seeing that how the models look like, how the other things are available over here, and I can see those things from here also. Uh, we talked about Wolfram Neural Net Repository, and then this is how you can just directly import the neural net from the repository into your Wolfram notebook, and then you can see the model over here, what are the inputs, what are the outputs, and you can see over here each layer itself is a net graph of 3 nodes. So if I let me just quickly import this, refresh this, and I can see I can click on any net chain and I can see how that net chain is being graphed or how the net graph is consist of and what are the architecture of each component or a sub-module over here. I can also use the net extract to also extract any specific module. So for example, if I want to see how this net graph is and I want to see it and study it or modify it only separately, I can click over here and I can see from here also below. But if I need to uh, extract this separately, I can use the next extract command and I can extract it separately and see it more in detail. Maybe I need to go in and make some changes or modify any certain things. I can do that. Maybe you need to drop out any certain types of layers from the this specific net. You can also do that. Let's take a look at this neural net, which is based on ADIN. So basically what it's doing is it performs style transfer by aligning the mean and variance of the content and style feature. So this net is trained on MSCOCO dataset, which has almost around 300,000 images, as well as painters by number, which is also a dataset consisting of 23,000 images of paintings. And you can have this neural net in your session, and then you can see that it comprises of like encoder content, and then there is an encoder style. So it has 2 inputs coming in after having certain chain analysis on each of this particle. It's coming into ADIN, which is another net graph. Certain more functionality is done that. Then there is a separate decoder module. So it comprises of certain things. You can extract each of these modules separately also. So what I'm doing over here is extracting the modules, encoder style, as well as the encoder content. And I can see them more in detail. Each of that in itself is a complete neural net in itself, almost around 30 layers in the encoder style, and the similar number of layers are happening in the encoder content. And then both of the input is passing through these two, and then I can extract the third module, which is the ADIN, and I can see and study what's happening into this module. What is the architecture of this neural network is happening over here. And then in the end, I can have the decoder, which is the last module, and I can see in itself, it's like 29 layers in that. And it all combines together, makes one neural net, which is illustrated over here. So I'll have one image coming as a content and one image coming as a style, performing certain types of functionality on that, and then I will get the output. And we can see that in this action over here. So this is my one image, which is a content, and this is the another image, which is coming as a style, and this passes through this network, and then it maps those based on the mean and the variance of the content and style feature maps. So this is what basically this neural net is doing. Another example we can see is about object detection. So this is also a neural net, which is the solving the process of locating objects in an image. So basically what it is doing, it will be finding a corresponding bounding box for the object, and it is based on this open images dataset, YOLO, which has like 16 million bounding boxes of 600 object classes on 1.9 million images. And this is a typical example of what this neural net does. You pass it an image and it will make in boundaries and give you what is the object in available. And there are 3 versions of this neural net available. Everyone has its own features. This is also available in Wolfram Neural Net. So what we can do is we can just import this model neural net into our session. We can see how this is, it has like 3 outputs. One is for boxes, one is giving the probability, what class this belong is, and the third is giving the object of that. So 3 outputs are coming out of this. Similarly, we have this function net information, and from that I can see what is the layer count. So there are like in total there are 349 layers in this net graph, and I can see the layer type counts as well. What layer is how many times used in this specific neural net. And then I can take this image and I can pass this image to this neural net, and I can see it gives me the boxes, the class probability, and that. And then because I'm working in Wolfram language, so I can write a small code to get the dimensions of this and then give it a proper image and get those boxes for that. But good thing is that based on this, you don't have to do all of these things separately now. In Wolfram language, we have defined a built-in function which utilizes all of this information and does all of these above things for you. So all you need to do is just pass it an image and it will give you the results for that. So it will tell you what the image is, what type it is, what is the location of this specific object in the image, and what is the probability that this belongs to this class. Or I can use highlight of the image and I can also have the over there. So it can identify this is zebra, this is elephant, and it does also know the locations for that. So you can get those neural nets and then utilize the Wolfram language to enhance it further for your functionality. So basically these gives you the probabilities of net results. Another example we can see is about semantic segmentation. So what semantic segmentation does is basically it's a pixel classification problem, and the goal over here is to find the pixel clusters corresponding to objects of the interest. So this neural net is based on ADMax model, which performs a segmentation on images into 21 categories. And it has it is based on only 17 residual units, and it is able to outperform any previous available much deeper architectures. And this is also a shallow and wide ResNet. So I can get this model into my session and we can see what this comprises of. So you can see it is a net chain, and then there are many net graphs, 8 nodes here in the second module, certain nodes. I can click on any of this module to see how the architecture of that specific module is and how they are contained together into a net chain. So I have an input with a size of, so these are color images of 504 by 504 metric size, and then it goes and give me the output classes, which are like 21 classes. Dimensions I can see from the dimension also. So these are 21 classes and the depth is 3. So I can just extract a specific module out of here, and I can see even a specific module is further divided into many net graphs. So, and then I can pass this image into this specific neural net and get the results out over here. So you can use this neural net specifically from the neural net repository. So basically what I've done in today's session is I have mostly focused on the neural nets which are used on images only. So in my upcoming sessions, I will talk more about on how to perform deep learning on audio and text data. So, but I will strongly suggest you all to kindly visit Wolfram Neural Network Repository website that hosts many models which are suitable for immediate evaluation or training or visualization and even for transfer learning. So you can get those models, perform transfer learning on them. So with this, I would like to thank you all for being with me today.